Tor Lacey here with a lecture about crustal deformation and mountain building. Like almost all active volcanoes, mountains are built along or near plate boundaries. This lesson will focus on non-volcanic mountains, like those we see here in the photograph, which offer us a great example of folded mountains. These form where the crust has been bent or folded upwards by tectonic stresses to create a mountain range. Here are the main learning objectives. Describe the geologic processes, the relative movement of plates, and the distinguishing landforms associated with each type of plate boundary. Relate tectonic stresses to plate boundaries, geologic structures, crustal deformation, and the building of mountains. Differentiate between constructive and destructive geologic processes and explain the energy driving these processes and identify examples of each. Describe the different types of contacts between different rock bodies and geologic structural features. Describe the relationship between stress, deformation, and structural features. Identify different faults and folds. Describe the interaction of rock bodies and structural features with Earth's surface. Interpret and create a geologic map. Accurately apply the term stress, deformation, or volcanism and plate boundary to describe the tectonic evolution of a specific mountain range, the Sierra Nevadas in California, for example. The geologically young mountains, those less than 100 million years old, are found along the margins of the continents surrounding the Pacific Ocean and along an east-west trending line through southern Asia and Europe. How are mountains made? In order to answer this question, let's consider a chain of events that can result in making a mountain. Deforming the crust means changing the shape of a body of rock by bending and/or breaking it. This happens when stresses are applied to rock, which typically happens along or near plate boundaries. Over time, stresses deform the crust into geologic structures, such as faults and folds. Through movement along faults and/or the bending of rock underground, the crust can be pushed upwards to make mountains. Mountains are also made through volcanic activity. Why does rock deform? Rocks deform because a stress is acting on them. Stresses are forces that push or pull or tear a body of rock. Earth scientists recognize three types of stresses: compressional stress, tensional stress, and shear stress. Compressional stress causes a body of rock to be squeezed. This mostly happens along convergent plate boundaries. Tensional stress pulls a body of rock apart in opposite directions. This would most be associated with divergent plate boundaries. Shear stress is a bit like tearing, where one body of rock is moved horizontally past another in opposite directions. This happens along transform boundaries or transform faults. So why all the stress? The rock making up Earth's crust is stressed out because of plate tectonics and the interaction of plates along plate boundaries. Divergent boundaries will produce tensional stress. Convergent boundaries, compressional stress, and transform boundaries will make shear stress. Though in reality, it's more complicated because all three stresses can exist at any of the three plate boundaries, depending on different factors, such as the shape of the plate boundary or the direction of movement of the plates along the plate boundary. Stresses cause deformation of the crust, which changes its shape through bending by plastic or elastic deformation and breaking by brittle deformation. Bending and breaking change the structure of the rock of the crust. Deformation changes the shape of the crust into structural features, which include folds, when a body of rock has been bent, or faults, when rock has been broken and shifted along a fault. How do we know if a body of rock has been bent or broken? We use a body of undeformed sedimentary rock as a baseline. Here we have an outcrop of sedimentary rock. In fact, the chances are that outcrops will be sedimentary rock because sedimentary rock makes up approximately 75% of all rock exposed on Earth's surface. As you might recall, sedimentary rock originates in horizontal layers known as strata. Considering this fact, we can use the horizontal strata of sedimentary rock as our reference or baseline. Where we observe that sedimentary strata is no longer horizontal, we know that the crust has been subjected to deformation. Plastic deformation makes folds and is always caused by compressional stress. Upward folded strata is called an anticline, while downward folded strata is called a syncline. The imaginary line around which the strata is folded is called the hinge or fold axis. The strata on either side of the hinge are the limbs of the fold. This is an illustration of an anticline that has been partially eroded along Earth's surface. Here's an anticline and some more falcons. Here's a syncline and a couple more falcons. This illustration outlines the progression of horizontal strata being deformed by compression into an anticline and a syncline, followed by erosion and exposure of the limbs of the folded strata. Strata more resistant to erosion may stand out topographically as outcrops of rock. When the fold axis has been tilted by tectonic stresses, the fold is called a plunging anticline or plunging syncline. This in turn will influence how the strata interacts with Earth's surface. If the fold axis is tilted from vertical, the fold can be described as an asymmetric fold. Brittle deformation makes faults and can be caused by any type of stress. There are two categories of faults, dip-slip and strike-slip. Dip-slip faults, also called vertical faults, are those where rock slides up or down along the dip of the fault surface. Normal faults are caused by tensional stress, while reverse faults are the result of compression. Strike-slip faults are either right lateral or left lateral and are both caused by shear stress. Here's another Cerritos College falcon, pointing out a small dip-slip fault. When naming vertical faults as either normal or reverse, the hanging wall and footwall sides of the fault must be considered. The hanging wall block is the block of rock resting on top of the fault plane, or the upper half of the fault. The footwall block is situated below the fault plane. Movement of the hanging wall, either up or down, will expose the fault surface, making a fault scarp. This photo shows a fault where the hanging wall moved downward along the fault surface. If the hanging wall moves downward along a dip-slip fault, it is called a normal fault. The hanging wall slides downward when tensional stress is acting on the crust. Here's a normal fault that moved very recently, producing an earthquake that you may have felt. If you were to visit the same spot 50 years from now, do you think the scarp would be as noticeable as it is in this photo? If the hanging wall moves upward along a dip-slip fault, it is called a reverse fault. The hanging wall slides upward when compressional stress is acting on the crust. This illustration shows compressional stress brittly deforming the crust into a reverse fault. Here's a photograph of a reverse fault. Note how the arrows along the fault tell us which way the hanging wall and footwall are moving with respect to each other. Strike-slip faults involve horizontal or lateral movement along the strike or compass direction of the fault. They are the result of shear stress and are classified as right lateral or left lateral. With right lateral strike-slip faults, movement of objects on the other side of the fault appears to be to the right. The San Andreas here in California may be the most famous right lateral strike-slip fault. If after a strike-slip fault is moved, objects on the other side of the fault appear to have moved to the left, the horizontal fault is called a left lateral strike-slip fault. Here's a photograph from a plane flying over a right lateral strike-slip fault that is offset strata in Death Valley National Park. Up to this point, we've been looking at structural features that are visible on Earth's surface. But what if a structural feature is below ground and out of sight? The only way to document the geologic structure is to make a geologic map. This is an example of a geologic map of Iceland. This is an example of a simplified geologic map of part of Wyoming. Like all geologic maps, this map was created using the orientation of the geologic units where they intersect the Earth's surface. The bands of color represent stratigraphic units or other types of rock. In order to determine the orientation of sedimentary rock units or faults, the strike and dip of these planar features are measured. The strike is the compass orientation of a plane. For example, the 605 freeway is a plane that is oriented north-south. To measure the strike orientation, a compass is used, and the measurement is expressed as an azimuth measurement or as a compass bearing. The dip is the amount a planar feature has been tilted from horizontal. This photo shows tilted strata dipping into the lake. This illustration shows a block diagram, A, and the same geologic structure in map view, B. On B, a strike and dip symbol indicates the strike of the strata, which is north-south or 000 azimuth. The dip of the strata is to the west, or 270 azimuth, and is tilted 35 degrees from horizontal. Below the block diagram are common symbols used on geologic maps to indicate structural features. Here is a block diagram of some real-world geology. Floating above the block diagram is how the structural features would be represented on a geologic map, based on the pattern rock units make where they intersect Earth's surface. For example, the strike and dip symbol that reads a strike of roughly north-south, or 000 azimuth, and 30 degrees west, is representative of strata tilting 30 degrees out of the ground and dipping to the west. After the orientation of the strata has been measured, a geologic map can be constructed, and the structure of the geology determined. In this case, the geologic map documents strata that is folded into an anticline and a syncline. This ends this overview of geologic structural features and geologic maps. You'll learn more about mountains and mountain building in the next lecture. Thank you for listening.